Next up, how to specify force distributions in FEA. Now that we know what stresses are and what is force intensity and how the force intensity depends upon normal, now we are ready to talk about how to specify force distributions in FEA. This is only the beginning. We will just talk to you about the core ideas. When you get to something more serious with regard to actually applying these things to a real situation with an actual problem, you will see more details. Okay, we have been exploring notation, meaning, stress intensity, assuming forces are known. But the way it works is all forces must be represented as distributed loads. So when we have distributed loads like contact or water pressure, we flip the script and describe the force using the traction instead of traction using the force. You're with me? So instead of taking force and dividing by area, we're going to take traction, multiply by area and integrate it to get forces. So what I mean by that is at every location on an exposed surface, we have to specify 3 force intensity functions. They are called Tnx, Tny, Tnz. You remember the notation? Tnx means force intensity on the plane whose normal is n in the direction x. Force intensity on the plane whose normal is n in the y direction. Force intensity on the plane whose normal is n in the z direction. If the plane changes, you have to change the n also. Okay, we are indirectly representing the force because we have to do this to compute the forces. We have to integrate. So if I take the x tractions and integrate, I will get the fx. If I take the y tractions and integrate, I'll get fy. If I take the z tractions and integrate, I'll get fz. That's how it works. Okay, it's not, this gets very painful if you have like curved surfaces. We are right now looking only at flat surfaces, but nevertheless, we can think of it this way. The main takeaway is that in finite element analysis, we always think of forces as the integral of the force intensity vector. So in finite element analysis or in continuum mechanics in general, force intensities are the primal thing, just like density is the most important, not mass. Like that, force intensity is the most important. Forces are the result of integrating the force intensity. Think of it that way. Okay, that's very important. Okay, so net force is the integral of the surface stress over the area. What do I mean? I have XYZ coordinate system. Fx is integral of Tnx, Fy is integral of Tny, Fz is integral of Tnz. What I mean by that is, let's say I have some surface and I'm applying all kinds of forces and I have a flat region here. And let's say I'm given that the stress field, notice stress field, which means stress matrix is constant. Let us say simple case. Okay, and it's given like this: 7 minus 5, 2, minus 5, 6, 3, 2, 3, minus 8 megapascals. So remember, each column represents one force intensity on one surface. Okay, now find the net force on the surface shown. So this gray colored surface, we want to find the net force on it. So how are we going to do that? Find the normal at each point on the surface. Now this turns out to be very painful if the surface is curved, but if it is flat, then there's only all the points on the surface as same normal. The normal is along the x-axis. So n is 1, 0, 0. Find the force intensity components. Stress matrix times for surface normal. Let's do that. Force intensity is T is 7 minus 5, 2. That's a stress matrix times the normal. That gives me 7 minus 5, 2. And then sum or integrate the force intensity over the area. Okay. So what it means is that I am going to integrate this. This is fairly easy because the forces are constant and the area is A. So I will get 7A, 5A, 2A newtons. This is how it works. It gets much more complicated if the normals changes, because then you have to account for that also, and you'll get some complex function. The stress matrix may itself change. So there will be a lot of complications as we go along, but this is the barest, simplest, most basic aspect. Okay. One last item. All of this was to get your finite element package to understand what you're trying to do. The real deal for you is to design something that will not fail. Okay, for that, you have to use what is called local axis to get more physically meaningful. All we did up to now was using everything with global axis. Okay, that is XYZ axis. But you really have to look at what is happening parallel and perpendicular to the surface. What do I mean? For interpretation of what the forces mean, it is better to consider the force intensity parallel and perpendicular to the surface at each location. You don't have to do it. You can always put the force intensity as a function of x and y. I told you it's a vector, no? So FEA packages will just use it as a function of x and y. They will never do that in parallel and perpendicular unless you come to some boundary and something like that. Okay. So surface forces, stress intensity, come in two basic flavors: push and pull, normal stresses, and slide or drag, shear stresses. Okay. So what it means is that we take whatever, so sigma I, can you see that's the force vector, and we resolve it, that's a traction vector, force intensity vector, and we resolve it as parallel, and that is the shear component, and perpendicular, which is the normal component. We don't have to do it. We can use the slanted blue arrow all the time, but it is convenient to break it up into the horizontal red arrow and the vertical blue arrow. Okay, in particular for interpreting failure cases. If failure occurs due to material separation due to pulling, that is normal stresses, then it is called brittle mode. Notice I did not say brittle material, I said brittle mode, because the same material may have brittle mode failures or ductile mode failures. Okay, most concrete, ceramics, clay typically have brittle mode failure under tension, but not all the time. Okay. The other one, if failure occurs due to material separation by sliding, it's called ductile mode. And this is determined by shear stress. So ultimately, we have to figure out which surface is going to fail. If I know which surface is going to separate, then I have to figure out what is the chance that it will separate through brittle mode, and what's the chance it's going to separate by ductile mode. And this usually is called a failure criteria, and we will talk about that in class later. Okay. By the way, we are done with all the things about stresses. There is nothing else left. Thank you very much.